You know, the terms that we use in science are used very specifically in science as terms of art, but they have very different meanings on the street, and this is a source of a lot of confusion. When scientists talk about fact, they're talking about confirmed observations. A hypothesis is a testable statement. You're saying, you know, what's the relationship between this and this? And you go out and test it, and you either accept or reject your statement of that relationship. Hypotheses are very useful. They're very helpful. They help us build theory. Theories are the most important things in science. Theory to a scientist means explanation. And these are logical constructs of facts, of tested hypotheses, of laws, of all kinds of stuff that, taken together and put in a logical descriptive fashion, help us understand some kind of natural phenomenon. Most lay people think that theories are guesses or hunches or something that you don't have to take terribly seriously. It's not such a big deal. Completely opposite in science. What a lot of, unfortunately, textbooks lead people to misunderstand is that a really good theory grows up into a law, as if theories are refined and then become laws, and laws are somehow more important than theories. In science, actually, what a law is a descriptive generalization. So we talk about the laws of thermodynamics that tell you about heat under different circumstances. You hear about the laws and study the laws of heredity that Mendel developed, law of independent assortment and so forth, because theories explain laws. So in general, the hierarchy of explanation is very different in science than it is in the general public. The general public puts facts on top, laws next, hypotheses, and then theories. Maybe theories and hypotheses can move around a little bit. In science, on the other hand, theories are the most important thing, laws are next most important, hypotheses are next most important, and perhaps the least most important part of a scientific explanation is facts.
It's not how theories. You have to understand what it means for something to be a theory. There's a lot of misunderstanding about that. If you have a new idea and you want to test it, that's a hypothesis. If there's countless objects and phenomena out there that have conduct or behavior that can be brought under one umbrella of understanding, and that umbrella of understanding allows you to make predictions that are then shown to be true, then you have a theory. This is what gives you quantum theory and relativity theory. You get all of this. In an earlier day, we didn't call them theories, we called them laws. But it's the same thing, okay? Same thing.
Sure.
If Einstein's theory is ever shown to be wrong, it will not be wrong in any regime in which it has already been tested. It would have to be a regime at the extreme limits of how it applies in the universe. And one example of that would be the center of a black hole. We know now that general relativity fails at the center of a black hole. We know in advance of that. We know that general relativity fails at the instant of the Big Bang. This is largely the effort of string theorists to try to come to terms with what those very special states of matter and very special times in the history of the cosmos. It won't be proven wrong because it's already been shown right. And if we find a new idea that takes it to those edges, that'll be a larger circle that we draw around relativity, but what's inside the circle of relativity will remain intact. That's what it means to be experimentally verified.
So what's a theory, and what's a scientific theory, and what's the difference between them, and does it really matter? Yes, yeah, it matters a lot. It matters a lot. A theory, defined, is a contemplative and rational type of abstract or generalizing thinking, or the results of such thinking. A lot of people think of theories as points of view. I personally have a theory that pineapple is a magical food that can be added to any other food, and while it might not make that food better, it will certainly not make that food worse. But oftentimes it will really make that food better. On the other hand, a scientific theory is a well-substantiated explanation of some aspect of the natural world based on a body of facts that have been repeatedly confirmed through observation and experimentation. To be a scientific theory needs 4 things: rigorous scientific testing, prediction and explanation, consistency, and parsimoniousness, the essence of being parsimonious. So let's say I have a theory that when I let go of this ball, it is going to float upwards. It's my theory. I can hold that theory. So when I subject that theory to rigorous scientific testing, but let's say that my theory was that within the confines of Earth's atmosphere, and with no special exceptions, when I release this ball, it would fall downwards. Now I can repeat my test over and over and over again and get the same result every time. But after rigorous scientific testing, I can start to form a scientific theory. Now, scientific theories are predictive and explanatory. I can predict, based on my scientific theory, that any object I release is going to fall downwards. I can also use my theory to start explaining phenomena in the natural world around me. I can explain why I'm sitting in my chair, not floating. I can explain why rain falls. I can explain why any object I drop will fall, and why the moon revolves around the Earth, and how the moon creates waves. I can use it for a lot of other pieces of science. Now we hit consistency, and I'm using that to cover 2 things. So, first of all, my scientific theory should logically fit into the scientific body that already exists. Now, sometimes it doesn't have to match up perfectly. Sometimes scientific theories will revolutionize a field, or other times they'll just make them a little bit more accurate. But my falling ball theory fits in with thousands of years of apples falling from trees, whereas my ball floating upwards theory, not so much. The other way I'm using consistency is for adaptation and modification. Guys, if we were in space right now, this ball would be floating, but that doesn't mean that gravity is wrong. You can sort of modify the theory of gravity to explain how in space things still are affected by gravitational pulls, but the different distances make the effect different. And the final thing you should keep in mind when formulating your scientific theory is parsimoniousness, which basically just means keep it simple. I could explain my theory by saying that this ball is being pulled towards the floor, which is being pulled towards Earth's crust, which is being pulled towards Earth's core. But it's just way simpler to say that the ball is being pulled towards Earth's core. And so once you've got a theory, you can start building other bits of science on it. Now that we know how things fall, we can try and overcome that. We can make spaceships, and we can make planes that can overcome this falling thing, or we can use falling to our ability. We can use weights and levers and all sorts of things. Scientific theories let us continue to expand science and explore our world.
Recognize that the very molecules that make up your body, the atoms that construct the molecules, are traceable to the crucibles that were once the centers of high-mass stars, that exploded their chemically enriched guts into the galaxy, enriching pristine gas clouds with the chemistry of life, so that we're all connected to each other biologically, to the Earth chemically, and to the rest of the universe atomically. That's kind of cool. That makes me smile. And I actually feel quite large at the end of that. It's not that we are better than the universe, we're part of the universe. We're in the universe, and the universe is in us.